All right, let's look at these conjugated dienes, and we're going to look at stereoisomers versus conformers. When we have our conjugated diene, note double bond, single bond, double bond. Note this double bond is trans and this double bond is trans. So you could call this a trans-trans 1,3 diene, or to be more specific, this is an EE13 diene. Note our double bond can be cis here and cis here, so that's cis-cis or ZZ13 diene. This one is cis and this one is trans. Yes. Cis double bond here, trans double bond here, cis trans ZE13 diene. And since you cannot rotate double bonds, the trans-trans, the cis-cis, and the cis-trans are stereoisomers. They are all stereoisomers of each other. However, let's look at this one right here. If we have double bond, single bond, double bond, what's the relationship between this? Well, note, to go from here to here, all you have to do is rotate this single bond. I highly recommend getting out your molecular models, making this 1,3 diene, and then note you can just rotate this and go from here to here very easily. So these are different conformations of the same molecule. These are not isomers. This is just a different conformation, just the same as we had in organic 1 between, say, staggered and eclipse conformations. These are just different conformations of the same molecule, but we're going to label this one. We're going to call this S-cis and S-trans. And don't be fooled. We've got the cis and the trans there, but realize they're just conformations. We call this one S-cis because if we draw a line down the single bond, we see that the two double bonds are on the same side of the single bond here. However, this can very easily rotate the double bond over, and now if we draw a line down along the single bond, the double bonds are on the opposite sides of that line, so it's trans, but it's S-trans. Note, a trans double bond cannot just rotate to form a cis double bond. That cannot happen. But S-trans can easily rotate to form S-cis if there's no other ring structure holding it in place. Okay. So, when we look at this here, we look at what's the relationship between this one, and this one. Well, the answer's on the page, but let's take a look. Cis bond, cis bond. Okay. Trans double bond, trans double bond. So this is cis-cis, this is trans-trans. These two are stereoisomers because you cannot convert a cis double bond into a trans double bond. Well, this is trans and trans. What's this one? Well, if we look closely, this is trans. Oh, and this one's trans. This is also trans-trans. Well, this is trans-trans. Therefore, these two are just the same. These are the two conformations. This is the S-cis conformation. This is the S-trans conformation of the same molecule. Don't believe me? Get your molecular models out. Build this one, and then you can see just with one rotation of the single bond, which can rotate, you can flip one to the other. They're just different conformations of the same molecule. Okay. So let's look at some properties of these conjugated dienes, and we've mentioned this several times before. I guess it must be important. When you have a conjugated diene, note we said this is the most stable resonance form, but you have these two resonance forms which are also available. They are less stable, but the whole molecule then, the resonance hybrid, is a combination of these three resonance forms, but since this is most stable, the resonance hybrid looks mainly like this, but the two less stable resonance forms have double bond character, have double bonds in between the two middle carbons, which means this carbon-carbon bond, single bond, is a little shorter than it should be. A normal carbon-carbon single bond is 153 picometers. Let's remember our measurements. 153 picometers, that is 0.153 nanometers. or what I like to go by, 1.53 angstroms. I like angstroms, this little A with a circle over it, because then normal bond, carbon-carbon bond length is 1.5. Oh, I gotta love the number 1.5. 1.5 angstroms, carbon-carbon double bond. I like that better than 153 picometers myself, or 0.153 nanometers. So, a normal carbon-carbon single bond is 1.53 angstroms. In our conjugated diene, it's a little bit short. It's 1.48 angstroms, or 148 picometers. So we can see that the resonance hybrid has a slightly shorter bond here due to the fact that these two less stable resonance forms that don't contribute much still have a little double bond there. And that's what gives your conjugated dienes their added stability. Conjugated dienes are more stable than you think they would be because of this shorter bond here due to the resonance. All right. Because of this, conjugated dienes can do reactions differently from isolated double bonds, isolated dienes. Also, conjugated polyenes absorb longer wavelengths of light. So you can have a diene, a conjugated triene. Recall with conjugation, you need alternating double single bonds. So a conjugated triene would be something like this. Double, single, double, single, double. That would be a conjugated triene. And it is more stable than any isolated triene, and they absorb longer wavelengths of light. And we're going to find out the more double bonds you have conjugated together, the longer the wavelength of light that gets absorbed. All right. I'm going to keep this video short because our next topic in the chapter is Electrophilic Edition 1.2 versus 1.4 edition. This is kind of a long section, so our current video is going to be a little short here, a little over 7 minutes, because our next video is going to be kind of long. I want to discuss the whole topic of Electrophilic Edition, which is very important and I kind of like it. I think it's kind of cool. All right.